is obviously Advanced Algebra 1 notes for Topic 8, Section 4. Company offers a rectangular pool, sizes, dimensions as shown. I don't have that shown, but I will. Each pool includes a deck around it. If Carolina wants a 15-foot wide pool with a deck, how many square feet will she need to have available in her yard? And so what we're looking at is a pool, and in the picture we're given that the pool is twice as long as it is wide. This is X and this is 2X, and we want to have a 4-foot deck. A 4-foot wide deck, okay, all the way around the pool. Then that means that this width will be X plus 8, and that this width will be 2X plus 8, or this length will be 2X plus 8. So the area of the whole thing would be 2X plus 8 times X plus 8. Okay. So basically, they're telling us that she wants a 15-foot wide pool. Okay. So if we look at this again, a 15-foot wide pool would indicate that the length would be 30. And then this would be 15 plus 8, or 23. And the length down here would be 30 plus 8, or 38. And that's where the 15 came into play, okay, from the original problem. This information was all given also. Okay, well, this and this, and the 4 feet. So to find out whether or not she has enough space in her yard for this, we just need to find the area of the whole thing. So the area of the whole thing would be 23 times 38, or 824 square feet. Okay. On the online homework, they might ask you to use the equation 2x plus 8 times x plus 8, and to plug in 15 for 8, or for x. Sorry, to plug in 15 for x. And so 2 times 15 is 30 plus 8 times 15 plus 8, which is the same thing we multiplied together over there. 38 times 23, we get 824 square feet. Okay. Vertical motion model is given by the equation h of t equals negative 16t squared plus v sub 0t plus h sub 0. And the v sub 0 stands for the initial velocity, and the h sub 0 stands for the initial height. Okay. And then when we have a problem, we plug those into this equation. And when we mean vertical motion, we mean, we throw something up in the air, it comes down. And it's basically a parabola that opens down, and that's why we have that negative in front. Okay. So h represents the height of the object in feet, t seconds after it's launched into the air. V sub 0 is the object's initial velocity, and h sub 0 is the object's initial height, as I just said. So a diver jumps off of a high platform at an initial velocity of 16 feet per second. So h of t equals negative 16 t squared plus the initial velocity is 16 t. The height of the platform is 30 feet, so that would be the initial height. So plus 30. And then we can answer any questions. How many feet above the platform will the diver be at its highest point? That means find the vertex. It's for a parabola that opens down. The highest point that's going to be achieved is the vertex of the parabola. So the vertex is the opposite of B over 2 times A, and that looks to be 1/2. We use the opposite of B over 2A, and then to find at what time that occurs, or the y coordinate, we plug in 1/2 for t, so negative 16 times 1/2 squared plus 16 times 1/2 plus 30. So this is going to be 1/4. 1/4 times negative 16 is negative 4. Half of 16 is 8. And it looks like I'm going to get 34. So the platform is at 30 feet. When the diver jumps up off that platform and jumps up into the air, he will be at 34 feet in 1/2 of a second. And so how many feet above the platform will the diver be? We have to answer the question. He'll be 4 feet above the platform because the platform is 30 feet and his highest point is 34 feet. So he's going to be 4 feet above the platform. Okay. Each year for the past 5 years, ticket prices for a school play have increased by $1. So the director uses the function f of x, and I see a typo there, it should be 7x squared. So f of x equals negative 7x squared plus 90x plus 750 to represent the relationship between the number of price increases and the average predicted revenue per show. How well does this function represent the actual revenue data and assess the fit of the function using the residual plot? So what they want us to do is to basically graph what's going on here, okay? And the graph will be the first graph will be along the bottom here. Will be the number of increases. So that'll be 1, 2, 3, and then along here we'll put the predicted revenue, okay? And what we can do, because it jumps up to 750 pretty fast there, what we do is we put a little cardiac symbol here is what I call it. And what that means is that I'm going to skip a bunch of numbers. So this number right here is 0, and I'm going to skip all the way up to 760. I'm going to change my mind. No, I'm not. Never mind. So I'm going to jump to 760, and then I'm going to count by 40. So there's 800, 840, 880, 920, 960, and 1000. Okay. So at 0, pricing, no price increases, going back to my chart, no price increases. Predicted revenue is 750. So it's going to be approximately here. And then at 1 is 833. At 2 is 902. At 3 is 957. And at 4 is 988. And so we want this to appear to be a parabola. Which I missed a couple of points, but it kind of does. And then it says we want to use the residual plot. The residual plot is this, okay? At 0, I'm at -5. And I'm not even going to put a scale here. At 1, I'm at 13. At 2, I'm at 8. I should probably get higher. At 2, I'm at 8. At 3, I'm at -5 again. I'm sorry, yeah, and then at 4, I'm at 10. Okay, so my residual plot might look something like this. And the residual plot when it shows both positive and negative residuals, that means that this curve generated by what we might increase the price or how many times we might increase the price is good. If everything on my residual plot was all lumped together here or all lumped together down here, that would be a negative correlation or a positive correlation, and we want some in both areas. Okay, and so the residual plot shows both positive and negative residuals, which indicates a generally good model. Okay. If we have time, and I'm not real sure if I'm going to make time for this, but we can also put this data into a graphing calculator and have it graph the regression plot for data. And it's what we talk about next is, quadratic regression. And quadratic regression is a method to find the quadratic function that best fits that model. And so hopefully, like I said, your homework for this section is going to be all on the worksheet. We're not going to do any online homework because they have a lot of calculator problems in there. So that's where we are with that. And that's all I have for that.